So good morning, good evening, or good afternoon, depending on where you are. It's my pleasure to introduce Cheryl Fillekes from the IBM-Z group. And in that organization, she ports system software to mainframes and investigates the application of AI and quantum computing to problems in glacial collapse and flood zone transportation logistics. Cheryl completed her Ph.D. in geophysics at the University of Chicago and did subsequent postdoctoral work developing numerical models of nonlinear processes in both the solid and fluid Earth. Today, she will discuss her research in glaciology and an overview of a recent conference held by the International Society of Glaciology. So without further ado, let me turn this over to Cheryl as she discusses with us perspectives on glacier and ice sheet collapse from the IGSOC 2023 conference. Thank you.
Thank you so much, Lloyd. This is, I've titled this Perspectives on Ice Sheet Collapse because it's basically my perspective or the perspectives that I gathered at the International Glaciological Society symposium on the Edges of Glaciology, which took place this past summer in Limerick, Ireland. And we'll first go to, here we have a menagerie of climate tipping elements. We're calling them tipping elements these days instead of tipping points because there are so many of them. The loss of the Greenland ice sheet, as you can see, and the loss of the West Antarctic ice sheet are considered potentially quite disastrous occurrences, along with all the other ones that you can see here. The boreal forest shifts. This was published in April of 2023 before the widespread wildfires in Canada and other horrible things happening around the world. So this is already a little out of date. The timings, these are the timings that are considered by the current, best estimates for how soon these things might. My husband teases me about, well, is it apocalypse now or is it apocalypse later or apocalypse much later? So this is an attempt to answer that question. These are estimates as to how fast these different types of bad things happening. Ice-free ocean in some summers, loss of the corals, shift of the Amazon rainforest, large scale. So it's trying to get one of the main uncertainties is what would happen if methane clathrates, hydrates were to be released, and the changes in the overturn of ocean waters. And they list the collapse of the West Antarctic and Greenland ice sheet as maybe taking place, near the end of the century. However, these are all estimates based on their individual internal processes, and they don't take into account the nonlinear interactions between them. So, for example, if there was widespread release of marine methane hydrates, obviously warming would take place much sooner and everything would shift to the left. And we want to at least know if that's happening, if it starts happening. So there's been a lot of interest in the collapse of the West Antarctic ice sheet in particular. I first learned about the West Antarctic ice sheet potential collapse when I was a graduate student back in the 90s from one of my committee members, Doug McHale, who goes down there every southern hemisphere summer. And at that time he was driving spikes in the Ross ice shelf and with little GPS units on them to see how fast things were moving year to year. and he was pretty terrified. You'll when you read about these things, what you're seeing here is the light gray area is all the grounded ice. The dark gray area is floating ice. So the melt, say this were all to melt, for example, that would not make any difference in sea level. However, when these glaciers and ice sheets retreat, what happens is that you start getting movement of this ice, or there is constant movement of this ice, and it exits through these ice shelves. The ice goes from the ice cap into the ice shelf, and then calves off and melts into the sea. So it's the ungrounding that is the most concerning. Over here in Greenland, there's also the color scheme is a little bit different. This is all grounded. This is all grounded ice. The dark gray here is exposed ground, but the bathymetry lines are the same. And then surrounding this, there's sea ice. And the significance of sea ice is that that you might have heard of recently in the press, is that when ice calves off from these ice shelves, it forms sea ice, and the sea ice, the effect of it is to, like, all these different chunks of ice keep they exert back pressure on these ice shelves so that they don't calve off as fast. So when you have loss of sea ice, that's also of concern, because it you can infer the increased flow of water out of this grounded area here, and potentially the movement of this line between the grounded and ungrounded area back into the as the sea level rises. So this is a problem, and I'm gonna go down to here. This is a measure of the loss of ice from the Antarctic and Greenland ice sheets between 2003 and 2019. And the change in ice thickness, you might hear, oh, well, it's increasing in the middle, but decreasing at the edges. So that's still a problem. So a meter a year is a lot. The amount of ice in Antarctica is around 27 cubic kilometers, 27 million cubic kilometers. In West Antarctica alone, it's around 2.7 million cubic kilometers. The estimates, which go back decades now, as to how much sea level rise would occur from the collapse of the West Antarctic ice sheet, are between 3 and 6 meters, which means goodbye Tribeca, and most importantly to the IT industry, goodbye the big data switches on Hudson Street in New York. There's kind of a picture of Hudson Street, Western Union building, but this is and the estimates for the if all of the Greenland ice were to go, is there's about 1.7 million cubic kilometers of ice here, and that's enough to raise sea level by another meter or so. So it's a worry. So the question is, how fast is this going to happen? I have put a number of references and notes in a Slack channel, which I hope that we can use for question, answer, and discussion. The name of the Slack channel is #ice-sheets-interest, and it's in the research Slack work group so that you should all be able to access it.
And Cheryl, I also put it in the chat just so people can just copy paste.
Right. Yeah. So it's happening. A friend of mine, Mike Beavis, went up to Greenland a couple years ago and noticed that that there were a large number of mechanisms that was causing this ice loss to happen, having to do with large subglacial lakes forming and then flowing outward from there. So the processes are quite complex and quite fascinating. So, and then in April, I was reading the newspaper, and as I do, and in the Washington Post, it says scary new data on the last ice age raises concerns about future sea level. What Christine Batchelor did was take a look at these ridges, which indicate surges of ice efflux, and owing to glacial boundary retreat and advance, and it indicated around, nearly 2/3 of a kilometer of retreat of glaciers per day during the last at the close of the last ice age, and these are also in the Slack channel. So this rather startled me. So of course I called my old committee member Doug and said, "What is this?" He said, "Yeah, it's bad." And and I noticed at that time that there was a symposium happening in Limerick that included all of the leading lights that study this process, and the abstract deadline had not yet passed. So I thought, oh, I should go to that and maybe hastily assemble some sort of thing to do to take a look at this. And yeah, so I signed up and got ready to go, packed my bags and headed out. And I'd like to talk a little bit about Andrew Fowler, who is running this. He wrote a book recently. I provided a link to this on glaciers and ice sheets in the climate system, which is pretty much the definitive, like it was published just this year. And so if you want to know about and each chapter is written by a different expert in the area. So it's terribly good. He also wrote a book that I read. Everybody wrote a chaos book back in the latter part of the last century. Andrew is one of the very few people that included a whole chapter on the formula on Hamiltonian systems, and with applications to geology and geophysics. So, I would encourage you to take a look at those if you're curious about who these people are and what gives us the right to model these things. So, my hastily assembled. You can't go to a conference empty-handed, right? And formulating some sort of model uh, raises all the pertinent questions in your mind. I thought, well, what can I at IBM do uniquely that other people can't? And I thought, well, these quantum computing, and so I formulated the crevasses and crack networks as using network X, not retwork X, but and then tried to look at how these cracks would connect with each other to allow these chunks of ice to crack off. And so you map the node attributes to take each of these nodes, map them to qubits, and then map the graph edge attributes to quantum circuits that connect them, set up circuits on our famous IBM quantum computer with those mappings, and take successive shots through the quantum circuit to determine which crack patterns are the most energetically likely, including calving. And it's suited to modeling episodic calving because it's, repeated cycles through the circuit, and hopefully to allow us to do some numerical stability analysis to see whether it's going to work or not. Now, the big unknowns, of course, and that I was, reading this new book that, I was like, I'm sure they have a table somewhere that tells us the constitutive relation of ice and what the boundary conditions are and how to formulate them correctly and what the flow rates are and the mass and force balance. And there's a lot of information in there about it, but they're still largely unknown. And one of the things I figured, well, they'll just tell me if I go to the conference, I can, people can tell me directly what these numbers are, what these formulas and numbers are, what the elastic plastic transition is for ice under different stress conditions, and, what I should use for my boundary conditions and flow rates and what the mass and force balances are. And it turned out that these are generally unknown in all forward models of glaciers and ice sheets. So that was fascinating. So the forward models that were presented, I won't go through any of them in any detail. They have finite element models that have been developed over the years and decades, finite difference models, and models of detailed boundary processes, which are, and then of course, because you want ground truth on any of the things you use for for the inputs into these, in particular, the constitutive relations uh, and the boundary processes. There were a number of reports on expeditions to measure the boundary processes, particularly like right at the shear edges, on the edges of glaciers, and going to the very submarine, going into ice caves and measuring what the shear is like at the base, drilling into the ice to understand what the historical processes are, what the shear stresses and strains are there at the boundary. And there were a number of experiments presented to determine the constitutive relations, ice, big chunks of ice that they're putting under, they're actually twisting them in these great big cryogenic chambers. And there were a number of developments in remote sensing presented by people from NASA in particular, both space and airborne remote sensing to determine the thickness of the ice, the height of the ice, the isostatic rebound where ice is disappearing. It was very, very informative, and a number of there was a statistical study done by Doug Bem, and an AI characterizations of ice sheet evolution, which I'm going to cover the AI characterization in particular next. And there will be a special issue of Annals of Glaciology to publish all of these in 2024. And I've provided a link to the abstracts and a number of publications that have come out since, specifically, well, on the AI characterization of ice sheet evolution, which I think is one of the more it's interesting because the all of these models, there's the constitutive relation maybe within an order of magnitude, maybe two. The boundary processes uh, have the same issues. So there's and then there's a philosophical issue, which is, if you try to model it holding the flow rate constant and try to figure out what the shear is at the base, for example, you now you have a model that resembles reality, but you can't really predict the flow rate. And if you hold make up something about what's happening at the base of the glacier and the far edges, in particular, and constrain there, then so what's happening is that these modeling techniques are not creating something that has predictive power. You can fit what you see, and see what the relationships are between these different processes. But what you're not getting is you can give a timing, but it's the assumptions are worrying, because you need to make assumptions in order to do any calculations at all. It's so I class these as mantle convection all over again, which was the feeling I got from it. It's very good stuff. The finite element model in particular developed a rule of thumb for calving that was very accurate, and was then fed back into these statistical and AI models. That so it's really the interaction between all of these, which is why it was so important for us to get together in person, to exchange our latest results. And so if you want to follow it, I would say this special issue is going to be pretty exciting. So I'm going to go down to the next slide. Okay, what I found to be the most interesting and potentially useful was using big data to understand calving in Greenland. And what Enzo Zhang, Jenny Catania, and a number of other people did was they composited Sentinel-1, Sentinel-2, and Landsat 1, 2, 3, 4, 5, 6, 7, 8 data to see if they could use machine learning to detect the leading edges of glaciers. And since you get a view of these things, every week or so, and you have a historical data going back a few decades. The idea was to use machine learning to detect the leading edge of the glacier and how it moves through time, so that you can know whether to sell your property in Florida yet or not, or whatever. The way they went about it, it was a supervised learning model where they manually labeled training and test data, and compared the two, and that allowed them to automate glacier terminus movement with this algorithm, which is published, called AutoTerm. And they were able to trace the terminus retreat in advance of many glaciers in Greenland, tens of thousands of them, through time, which is, of course, informative to the ice sheet thickness decrease, the amount of ungrounding that's taking place, and so forth. So they published in August, which is just a few weeks ago, it came out, what they presented at Limerick, so that you can go and read it for yourself. They talk a great deal about how they handled the problems with clouds and the Landsat data, and cleansing of the data, and so forth. Enzo Zhang, unfortunately, could not make it, because as a Chinese national, he was worried about whether he would be able to re-enter the country. So there's those things going on as well. Anyway. Oh, oh, there we go. They furthermore identified 3 regimes of calving that are clear in the textures of the surface of the ice through time. So there's the propagation of surface cracks in tension upstream, which lead to this sort of tabular, the ungrounding of, Rhode Island and Manhattan sized chunks of ice that go floating out into sea. And then there's this buoyant flexure at the edges. Of course, you have tides and you have swell, which flexes the ice and eventually cracks it, and it comes off in these icebergs. And then there's another interesting sort of regime of vertical columns of ice called seracs, which can collapse as well. And they form this more granular texture of just like instead of having these massive icebergs, you get these tiny little chunks and they just float out to sea. So one thing that uh, they had not considered, and which I suggested, was using the textures of the surface of the ice and applying AI to these textures, and determining, being able to automatically automate the process of identifying these different regimes of calving in the Landsat data. As you can imagine, it's absolute massive amounts of data. And I was like, Ginny, why don't you do this in Antarctica? And she was like, oh gosh, they're having significant data storage issues in particular. And one of the reasons I wanted to present this to an IBM research audience in particular is that this is one of the areas that IBM excels in, is providing massive data storage that can be addressed, and then you have memory issues when you go and try to process these huge Landsat scenes at once. So they were actually sort of struggling with their AWS implementation, and it occurred to me that if we worked with them, we could provide them with what they need to be able to apply these terrific algorithms and other algorithms and more machine learning to, and even AI to identify these things in an automated manner, such that when things start happening in one glacier versus the next, instead of studying this guy studying that glacier and this person studying this other glacier, you can have a balanced view of all of the processes at once, and make some conclusions, or know what's happening in Antarctica in particular. So the other thing that's been happening that I've been following since April, in fact, is this is Zach Laib's. I published or put in our Slack channel a link to his many visualizations of Antarctic and Arctic sea ice. And remember, I mentioned the importance of sea ice in terms of keeping these processes a little bit under control. If it just starts to break away and float out to sea, or melt or disappear for whatever reason, it can prompt an acceleration of this ungrounding of ice shelves processes. So this is the anomaly from the average. Every year it's a lot, a little, a lot. This year it's been the sea ice has been just unprecedented. The loss of sea ice around Antarctica, and this is the first time I've seen. Usually you hear phrases like faster than previously expected, or surprising, and now the verbiage seems to be moving towards scary and mind-blowing, which is bothering. And the other thing is that as well, observationalists, people that actually go there and measure these processes in situ used to speak in terms of centuries and millennia for the processes like the potential collapse of the West Antarctic ice sheet. They're moving towards timing. They talk in terms more of years and decades, which is yeah, it's a problem. So I think it's definitely a worthwhile area of study. And that's all I'm going to say today because I don't want to get myself in too much trouble. This is a picture of one of these way up glacier cracks forming, where this is a crack forming from the ocean up, but then you have ones that form, back here too, which result in the, calving of very large tabular pieces of ice, hundreds of meters thick, floating out into the ocean. So I invite you to the Slack channel and I would like to entertain questions now and discussion.
Thank you, Cheryl. Really appreciate the perspective on this important problem. So let me open it up to questions. I mean, I have a couple, but I'd rather defer to the others in the session. Well, with some silence or shyness, let me.
With shock?
Yeah, no. Well, yeah. I mean, admittedly, there's. I mean, this is why I thought this subject should be an important one for the for this audience because it's not an area that there's much familiarity among the the scientists and engineers. As opposed to other areas like those of us that are coming from the atmospheric side of things. So. One question I had, this was on the work that you pointed out to about detecting the leading edge of glaciers and the dynamics. Did they only use the imagery that's derived from Sentinel-1A and 1B, or do they also use the interferometric observations from the synthetic aperture radar, to examine sort of the subsurface?
Yeah, they used SAR data as well.
Oh, yeah, no, that is SAR data. And I was wondering if they're using the interferometric data, which is not the imagery.
Okay, I don't remember. But there's a lot of I don't remember.
Okay, yeah, and I also had a similar, being familiar with the sensors and the spacecraft. I was wondering if the authors ran into any issues with polar coverage, given the orbit geometries of the spacecraft.
Yeah, they only have the data that they have, and
Okay.
it's more around the edges than right in the middle.
Right, yeah, because they're particularly for the visible imagery, they're it's designed with some sun synchronization, so you have common passes over with similar daylight. Well, obviously an issue in the polar regions.
Yeah, the bulk of the paper that they published and the bulk of the time that they spent in the presentation was in data cleansing. I think that cloud cover was the biggest issue.
Yeah, certainly for the visible imagery, makes a lot of sense.
So they had ways of automating that, and they were exploring AI to do that as well. So
those were the primary questions that I had. As a side comment, earlier in my career, I did work with the Nimbus 7 spacecraft, so I'm showing a little bit of vintage here, and but with the Simmer sensor was one of the probably the first one to really be able to do remote observations of ice cover. That was launched in late '78.
Yeah, yeah. And at least you don't have to pay $3,000 a scene now, like during the Reagan administration.
Yeah, it would be interesting to see if some of the commercial providers these days are, have good polar coverage. But I suspect that, I don't know how big their market would be for those, for the polar regions. But uh, yes, so are there any other questions for Cheryl today?
I would have a question about the guys who have problems with the large amount of data. Or maybe it's not a question, but I know that the team around Thomas Brunschwieler in Zurich just submitted a paper about exactly that specific problem, where we have, but in a flood related context. I don't know whether you heard about that.
Yeah, I did my Watson X challenge on using that data. I got some for yes, and it is amazing how much data there is and how computationally intensive it is to just move it and analyze it to extract an interpretation. Um, what I did was I took their flood model and applied it to an area in the Mohawk River Valley because I know which roads do flood out, um, and overlaid it with a road network and did some recalculations of routing between farms and distribution centers, mostly because that's what we on our farm need to do is get our products to um, the distributor warehouses, and they're very often on the other side, where they all are on the other side of the river. So getting it there in time of flood is an issue, and if it's that kind of a problem for us, when you have far more devastating floods, um, being able to get emergency vehicles in and out, even between major cities, if they still exist, is it's the logistical problems are affected, of course, by the flooding, and you do have to recalculate your routes or also determine things like how isolated are different communities by floods, historical floods, that you can apply this algorithm to. So, yeah, the hands-on was very instructive in that, and it applies to ice sheets as well as to flood zones. So thank you
so
for asking.
okay, so were you talking about the foundation model, or
Yeah.
because what I referred to was the recursive segmentation algorithm. I think they just submitted a paper like 2 days ago or so.
Wow.
Um, and so the idea behind that is that you don't need to process every pixel of the complete Antarctica,
Mm-hmm.
but rather take a low resolution shot, analyze it, and try to figure out where should I zoom in, and do
Mm-hmm.
this over and over again. And that is or saves a lot of computation power. So I just thought maybe that would could solve the problem you described earlier with the guys on AWS.
It may well, and if I'm, people are always hesitant to circulate their preprints, but I'm hoping that internal to IBM, we would be able to, if you tell me who they are, maybe I could, take a look at it and alert them to this. I don't think, I wouldn't want to send anything pre-publication, but make them aware that there is this algorithm that they could apply to.
Yeah. I can send you the team's names via Slack if you like.
Sure. If you put it in the ice sheets interest group, then I'm trying to consolidate I think I'm in like hundreds of channels, and I'm trying to keep things organized by topic these days. So, and people drop off the DM, so it's just like finding them again can be a
Okay, yeah.
the problem. So yeah, I would appreciate that very much, Tobias.
And Neil has his hand raised for a question.
Hello. Hi, Cheryl. This is Neil from Poland. It's nice to speak to you.
Hi.
Thank you for a fascinating insight into the modern ways that science have been used to conduct research on the ice sheets with the big data and AI and lots of modern tool sets that we have now.
Mm-hmm.
Different from the old sampling of ice that we've seen in the past. Ice cores are obviously still in use and they still have a valid place in the science, but I see the new tools being introduced now. It's not a very scientific question for you. These very cold areas of the world have often attracted adventurous explorers. Some of the first people to report back on changes in the climate were explorers originally. Have you ever had a chance for a nice visit to some of these cold polar regions? What's your experience of visiting them?
Nope. I have never gone there. I go cross country skiing out my back door on our farm. That's how I get up to the cabin here on our, in our woods. That's about as far as I get into the ice and snow. But Doug, on my PhD committee, spent a great deal of time there. He's in his 70s now, so he's not going down as frequently anymore. But I would say about 70 or 80% of the attendees at this conference had either gone on expeditions to Greenland or Antarctica or Alaska. And many of them spent a great deal of time on the glaciers in Europe and South America and so forth. It's I mean, it was a really fascinating, like stories of, large pieces of expensive equipment falling down crevasses and rescuing the people, and not all of the people surviving terrible accidents.
It's a very
Yeah,
harsh
so
environment, yes. I've only been to
it's a
alpine
very
glaciers
harsh
myself.
environment.
I've never been to an ice sheet myself, so I hope maybe one day that you would get the chance to step outside your models and have an experience there.
Yeah, I have been on a glacier in the Parc Mercantour in the south of France. So that's my experience with glaciers, is walking around in the on the glacier there. So
Well, thank you for your time. Thanks, Cheryl.
okay.
And Neil, just for your excuse me, just for your reference, we did have an IBM speaker in this series back in March, Mark Stevens Rowe, who earlier in his career worked for the British Antarctic Survey.
Oh, right. Okay.
Yeah. So he's a meteorologist, so his perspective was above the ice. So it's a common bias that a number of us have.
The closest I've been is I own a book called The Winters of the World, which is edited by Dr. Brian John, which describes all the previous ice ages. So I've very much enjoyed my bookshelf and living in those worlds through the words of these books and through Ernest Shackleton's books and various other books about Antarctic exploration. So I find it fascinating. So it's very nice to listen to you. Thank you.
Oh, no problem. there's a documentary that came out 10 years ago called Chasing Ice, which it's actually quite useful if you want to get an idea of how complex the boundary conditions are, because they're looking at the calving processes in quite a lot of detail over time, and also running around on the surface and, looking into the crevasses and going into the ice caves, which is massively dangerous. Um, yeah, so it's not out of there was a moment when I was a graduate student when I almost signed up with Doug to formally be his student so that I could go to Antarctica, but I got caught up in mantle convection instead. So in modeling, deep earth interior processes where you can never go, unless yeah. So I appreciate the importance of going there. As an aside, one of the other areas that were looked at that are an active area of study from the perspective of understanding the basal boundary what happens at the base of an ice sheet as it moves across a landscape, is looking at drumlins as they exist, because as ice sheets advance and retreat, they leave behind little piles of rocks and dirt, and they have a very distinctive teardrop shape, and there's theories and models of their formation and what that means about the stress and strain conditions at the base of an ice sheet. And there's drumlins all over the Rochester, New York area. Our farm is literally on a drumlin. So, maybe we'll have our next glacial geomorphology study, digging into the um, digging into the ground here and looking at the various layers of rocks. There's a lot of glacial erratics, as you can imagine. Those are big boulders that are just like left behind, and an interesting mix of different kinds of rocks in various levels of erosion that are quite distinctive of things left behind by glaciers. Terrains, whole landscapes left behind by glaciers. So as we drive our yogurt and vegetables out to our distributor, which I get to do on the weekends sometimes. I'm in the middle of drumlin fields and terminal moraines, and it's just it's fascinating imagining what it was like in this region at that time, and studying these terrains is another active area of inquiry for understanding how ice sheets uh, uh, advance and retreat. Slightly safer. I only have to worry about bears and so. Well, thanks a lot, everyone. I've got to drive to Poughkeepsie now. I hate to cut you short, but there's I would appreciate any and all contributions of your perspectives on this fascinating problem to our to maybe an interest group if there's a growing interest. I would in particularly just love to be able to gather some of these. This Landsat imagery is all available on, interestingly, most readily on a European website run by Copernicus. And that's what I used to do, the flood thing. So yeah, I hope that there's interest at IBM and getting substantial computational resources. When I said that they were limited by, it's not just the algorithm that they're using to access and analyze it. It's just that there's more of it than if you were to analyze all of it at once, you would need a large fleet of mainframes. So I think that in the era of distributed computing with little x86 systems, the appreciation for having, you know, terabytes of main memory, and you know, as people aren't quite aware that that's a possibility, and now having, you know, terabytes of main memory in combination with GPUs that are sitting, you know, hundreds of GPUs that are sitting right on the L2 cache shared with the CPUs is, I think that there's a lot of things that could be done with the Z16 in particular that would help these problems, the pipeline be something that would be more readily achievable, and possibly not possible to achieve with our competitors. So that's one of the reasons I was so excited to share this with this audience, you guys. So.
Oh, Cheryl, I want to thank you very much. I know you have to run, but want to appreciate everyone's questions and participating this morning. And so let's continue the discussion in the Slack channel that you've set up, especially since you do need to run to Poughkeepsie. So thanks again, and thank you, everyone. Have a good day, and we will talk again in our next session in a couple of weeks. Thanks again. Bye-bye.
Okay, thanks. Bye.
Thank you. Bye.
Thank you. Bye.